right, so the theme of this morning's talks is processing of memory, and Phil Gibbons will lead off.
All right. So key takeaways of this talk, all right? I always like to let people know what they're going to hear. Data movement is a dominant cost in computing. Processing memory reduces it. I'm going to talk to you about how the PIM situation as sort of a model of computation has some uniqueness to it. It's not exactly, it's sort of a combination of shared memory and distributed memory. And I'm going to talk about the model of computation we defined. I'm going to talk about the inherent tension whenever you're pushing compute to memory between load balance, communication, and skew whenever there's and space whenever there's a skew in the workload. I'm going to do a case study on a data structure we call PIM tree, which is an ordered index. I'm going to try to do that in a way that doesn't steal that much of the thunder from Hongbo, who's going to talk about that in more detail after me. And then just a slide or two on some of the other things we've been looking at, and then some things about open questions and where we're headed. OK, so processing in memory as an idea is 50 years old, basically. There's a paper by Hal Stone, right, 50 years ago that says, oh, what if we put some compute near our storage? It's an idea that kind of resurfaces every decade or so, or a couple decades or so. And so then the question is, like, OK, why are we resurfacing it again, right? And I think that if you've been at these talks, at this workshop, or this special year from the beginning, you've heard speaker after speaker at the boot camp and earlier this week try to convince you of that. Okay, so I've sort of removed the slides I would normally use to sort of get us up to speed on processing memory because presumably most everyone here has seen it. But the bottom line is that moving data is really expensive, okay, in terms of energy costs, if nothing else, right? And so you could throw a lot of energy at it. You can have GPUs or whatever. You could throw a lot of energy at it, a lot of expensive hardware at it to make data movement maybe not affect end-to-end performance as much, but it's still going to be an energy hog, all right? And so the idea is that if compute is cheap and data movement is expensive, let's push the compute. Let's close that distance, right? Let's make it so there's less data movement. Yeah.
So yeah, I've been wondering this because I've heard the other talks and this, this theme. So how is it? Do you know how this accounting is done, right? So you take data and move it from memory into processor. Like, at what point is it and then you process it? At what point is it processing? At what point is it data movement?
So the data movement is sort of getting it. Well, even just getting it on the chip that the processors is sitting on is already really expensive. But it's often measured like if I move it into a register. So if I want to do a multiply of two operands, what's the energy cost of just moving those two operands into registers? And once it's in the register, the processor can just run internally and not
Once they're in the registers, then you're charging that energy to the process.
Yeah. Once you do the arithmetic, start the arithmetic part of it. The functional unit that's doing multiplication kicks in at that point. Okay, good. So why now? Basically, as the previous speakers have been talking about, there's things like people starting to care a lot more about energy, right? It's not just end-to-end performance that matters, but also there's more and more sort of devices that are being produced, right? There's products you can buy that do processing in memory that there weren't necessarily before. We can talk later whether that as an industry is going to survive or not, but they're out there. Part of that is the because of the influence of GPUs and other accelerators, there's more of an appetite for heterogeneous hardware than there was before, right? For a long time, just homogeneous CPUs, that's it. That's all I want to deal with. But then, because it simplifies my life, right? If I'm writing an application, I only have to worry about one type of compute. But now we've sort of given in. We said, oh, okay, we got to have GPUs, and maybe an accelerator does this, an accelerator does that, and it's sort of baked into our platforms now, right? And so the tolerance to have something, that's not just a homogeneous CPU is also increased as well. Okay. Okay. And in addition to saving data movement, saving the energy cost of data movement, you can get low latency, right? So if the compute is sitting there on the same chip, or even in the same DIMM as the memory, then you get really fast response times. And if you put these things in all the memories, then all your memory components, all your memory banks, for instance, then it scales, right? As you increase the amount of memory in your system, you're also increasing the amount in which you can access that memory, because you're providing a means of accessing it that's on chip and scalable. It's not limited by these memory channels that we heard about in the these narrow pipes between chips that we've heard about in the previous talks. Okay, so so we're going to focus on sort of there's a lot of different flavors of it, especially if you went to the boot camp. You heard a lot of different flavors of how processing memory is going to work. What we're focused on in this talk is probably more rightfully called near data processing, right? We're not going to go inside the workings of the DRAM, that we saw in some of the previous talks, and mess with that. I mean, my group has done some work in that area in the past, but that's what this is about. This is really about you have a host CPU, right? That's your traditional front end, right? It's got a bunch of cores, got caches and things like that, and some DRAM. And we'll call that the CPU side, the host side. And then you have the PIM side, okay? Which, in the absence of PIM, is just a bunch of these, memory chips, right? Memory modules. But now we actually have some processing in them, okay? And all the communication in the model we're going to look at goes between the two, right? That basically, just like in traditional things, the CPU orchestrates what's going on, and the memory is sort of more passive. Now it's not completely passive because it's going to do compute, but it's all going to be sort of under the command of the host front end.
So like both of those sides look like they have processing and memory, but like the CPU side is more emphasis on the processing part and the memory secondary, or like?
Yeah, that's a good question. Yeah, I don't have the slide until much later in the talk, but basically, the way we view it, and you'll see in a minute, is that ideally, the host only touches its last level caches and so forth. So it only touches the stuff it already has on chip. Now it turns out in the real systems, it also there's like ordinary DRAM it can go out and access, and we would consider that already data movement. It's data movement if you go to the memory that doesn't have processing in it. It's data movement if you go to the memory that does have processing in it. Okay, but that's, I think, an important distinction in our mind, right? That there's two types of memory access that are fast. One is accessing the cache on your chip, and the other is this. Yeah.
So how powerful are these cores that are co-located with the memory? Are they sort of identical to the others, or are they sort of simpler and not capable?
So in the UPMEM, I'll give you the answer. So the UPMEM system, where if you're going to put the compute on the actual memory, you're very, and as I mentioned in a previous talk, these are very low margin industries, right? So they can only afford to stick in like very simple in-order cores, right? And because they're constrained by cost, they're constrained by power consumption, they're constrained by area, right? They've got a form factor, right? In fact, UPMEM, in order to put in the processors, they actually have to remove some of the memory. So their chips have less capacity than their competitors' chips, right? And so they have to make that worth it, right? In other settings, for instance, if you leave the memory as it is, and but somewhere else on the same chip, like in some sort of memory controller logic, and we'll see an example of this at the end of the talk, you have much more freedom to put a much more powerful processor in there.
If I move from like the memory to outside the memory to the compute thing, and then I move on until the CPU, how much of the energy and time is spent to get things from the memory, just outside, and then how much time is taken to get to the CPU? If, for example, it's 90% of the time and energy are just used to get out of the memory to the computing that's near it, then 10% of the time is used to get to the CPU, then there's not a lot to gain
Right,
from
right. This was
Maybe
actually.
summarize that.
Oh, yeah. So I think if I were to summarize it, it's saying that even if you have processing on the same chip, right, on the same, you're still reading from, the memory technology hasn't changed. You're still reading from DRAM, right? This is DRAM technology. If that's the expensive part of data movement, then this configuration hasn't helped much at all, right? That's the question. And it turns out that, that yes, this is somewhat expensive, but it's not nearly as expensive as the rest, right? That basically it's the power to get this off, along these connectors, get this off the chip, get this sent across whatever to where the CPU is, and bringing it that way, right? Yeah.
I think I have a related question, which is like, I should think of each core as having access to a private subset.
Yes.
Of the, right? So
Yeah.
the bus I can design is much simpler, and I don't have any sort of coherence between
Right.
cores, right?
Yeah.
So those are all things that probably make the transfer time, in addition to distance, things that contribute to power and time getting off,
Yep,
off
yep.
the chip. Okay.
Yeah. And people have measured this. So Oner Mutlu, who from ETH has done probably more experimental studies than anybody on these kinds of devices and other related PIM stuff. And so he's got papers that measure all these kinds of things. Yeah.
There was a talk yesterday on TLP. Where does that fit into this architecture?
So this is all physically addressed. Okay, so there's no TV over here. Yeah.
So does that mean that are these cores capable of doing any kind of computation, or is it specific, like only?
Yeah, that's another good question. Basically, the reason that this is exciting to us is that you can run arbitrary C code on here, right? So but a lot of the vendors are just doing AI accelerators. The only thing it can do on chip is some sort of AI acceleration. Okay. So we'll see how how things play out. But to us, it's far more, as we're designing algorithm stuff, it's far more interesting to have general compute here. Now, again, because of the constraints I was talking about before, this particular processor, doesn't have floating point, doesn't have SIMD. It's a very, just can do integer stuff, right? But in other configurations where you don't try to squeeze it on this exact in form factor, as we'll see at the end of the talk, you can have multi-core, you can have things like that. But you won't have one of those for each. The scaling of that is, instead of having, there's 2,500 or 2,000 of them, they can be up to 2,500. There's 2,000 of these things in the UPMEM system. In this other style of system, which is a much more coarse-grained system, maybe you have 64 of these things or something. Right? It's a much different scaling.
I think you just answered my question. There are no floating point exceptions to worry about, and no other exceptions either that could get thrown.
I think it's you can certainly have exceptions. I don't know. Does Hongwu Yue know what it's? These are two of the students. They're going to talk in a minute. Do you know what kind of exceptions it can handle? We'll have to get back to you on that one.
Okay.
All right, good. Okay, so So good. So as I mentioned, PIM is a very popular topic. Sort of gains a lot of momentum. 50 years old, but it gained a lot of momentum leading up to 2020 when we started thinking about these problems. And so I looked in the literature and hear these talks, and there's like hundreds of papers. There's like an entire, fervent activity in the architecture community, computer systems community, and so forth. Okay, and maybe a common theme of this workshop is, where was theory, right? We could only find 2 papers as of 2020 when we started doing this work that had anything to do with an algorithm or theory. Okay, so it seemed like that data movement is fundamental. This is like a fundamental question. We don't know the form factor it's going to take, but we do know that people are going to continue to want to do processing in memory. We need some foundational work on it, right? Okay. Yeah.
Works. So who manages what data is going to go to PIM and what data is going to go to DRAM? So is this, you have a virtual memory and some of it is going to go to actual memory DRAM and the rest, I don't know, or the user has to say, these are the data that I'm going to place in these PIM modules.
Yeah, it's all under control of the programmer. Oh, sorry. The question was who controls what data gets put in the processing and memory part of things, and what data gets put in the normal DRAM. So a related question would be sort of who orchestrates the action of the system, and it's all done by the user's program. So the user actually writes one program that's going to run on the host front end, and then a bunch of programs that are going to run on the PIMs. There's an API that says, I can load a program to all the PIMs, right? And then there's another one, I can go back later and launch a program to all the PIMs. There's a scatter and gather primitive. Scatter would say, I've got all this data sitting on the host, and I've got it designated for which PIM module it should go to. Okay, go. And so then it just spreads all the data feeds all the data to be in the processing memory enabled things, and then gathers the opposite, right? I've got some results that we produced. Let me gather them all back to the CPU front end.
Write data, you have to use specific interface to go to the specific module. It's not through DRAM. It's not through virtual memory, right?
Right. It's sort of an explicit offload and pack. Now, as I mentioned, the programs on the PIM are just normal C programs, so they're just doing reads and writes, and things like that. Yeah.
So it sounds like distributed memory programming is the style, basically, that you use. Is that right?
You're going to lead into my next few slides.
Okay, because there's been a lot of algorithms in theory work on distributed memory algorithms.
Yep. So that was our first question. Like, it looks different maybe from a systems, but let's drill down. Now, is there anything, we have tons of results that show this model of computation can emulate this model of computation, and so that allows us to take algorithms that were designed for world A and run them in world B, and they do just fine, right? Is that the case here? Okay. So that's what we set out to do, look at. And I'll get back to the question about distributed memory in a second, but let me just describe the model that we came up with. Okay? So there's a CPU side and a PIM side, right? The CPU side has a bunch of cores, and it has a shared memory that's of bounded size M. Okay? There's some network, and then you have all these local PIM things that have a core and some local memory, and the overall amount of memory is divided evenly among those. Okay, and all the communication goes through the network, so there's no direct communication this way. Okay, it all goes back and forth this way, and you do it in bulk synchronous rounds. Okay, you offload this work to do. You say go PIM side. It does a bunch of work, and then you there's a way of detecting when the PIM side is done, and then you say, okay, gather all the results back, and so it's these bulk synchronous rounds. Okay, so this is very natural, right? We're used to bulk synchronous worlds, right? But if you go to the to the documentation for these systems and stuff like that, they don't talk about bulk synchronous, right? So the thing about bulk synchronous is it tells us that what this network has to do well is take a whole bunch of things and route them, right? It's not routing a single thing, right? We have a batch of things and we want to route them, and we're going to wait for that to finish and then go back, right? And so this was very natural with our theory hats to say, oh, this is like, this should be modeled bulk synchronously. Let's not worry about individual messages, independent individual messages here, because that doesn't make sense for the system, right? If you're going to get any sort of use of this parallelism, you've got to be sending a whole bunch of things at once. You've got to be using these bulk scatter operations, right, and bulk gather operations, and run this whole thing bulk synchronously. Okay? And then in terms of metrics, we said, okay, so this is, as I mentioned, this is sort of a shared memory with a small amount of memory, a limited amount of memory. And this is what's noted, this is just like distributed memory, okay? And so what we did is we just combined the metrics of each, right? So on the shared side, you measure work and span, right? How much work was done over here, right? And what's the length of the longest critical path? And that's the computational metrics over there. And on this side, right, we want to view this more as distributed memory. And what you care about in distributed memory is, particularly in a bulk synchronous setting, is how long did you have to wait for the last guy to be done, right? So you need to take a maximum over what you made all these different sides do. And the two things that could constrain them is how much data did they have to receive or output, right? And how much work did they have to do, right? So how much communication was needed here, and how much work they had to do. So we called the PIM time being the maximum work on any PIM processor in each round, okay? And I/O time, the maximum number of word size messages from to any PIM module in each round. Yeah?
So do you have P different instruction caches for the processors in memory?
Yes. Yeah. But the typical way you program this thing is you send them all the same program, but you don't have to. Yeah. And so again, I want to keep separating out what the UPMEM system does versus what we're trying to abstract away as a model of computation. As a model of computation, we assume that you can run pretty much anything here, right? We don't care about that. In the reality of the UPMEM chip, they have a very limited instruction memory window, and that was a problem for us. You have to keep, if you have a complicated algorithm, you have to keep swapping in and out the code. Because in their generation 1, they didn't put very much instruction memory. So you get bit by those things in practice, but yeah.
Should I really think of this as being sort of 3 phases in the bulk synchronous approach where first you're taking a max over all the data in, and then you're taking a max over the processing time, and then taking the max over all the data out? Or are they able to sort of hide some of the computation underneath the I/O?
It sort of ends up being a max of each. I mean, it's only for theory. Theory, it's only a factor of 3, right? It's a constant factor, so we don't care about that too much in theory. But yeah, the issue, the real issue is that, and I think this was mentioned in one of their earlier talks earlier in the week, is that they don't have any coherence in this memory. So what they do is they just say, okay, you're either in a phase where the host can alter the memory and access this memory, or only the PIMs can access their memory. Okay, and that creates that sort of secondary,
So
this in the stages that I can actually buy such a machine, or this
Yeah,
is
yeah.
like
Yeah,
simulator?
for several years now, yeah.
Ah, I
Yeah,
can buy it and
that's the good news. The bad news is that as a startup, this company was acquired by Qualcomm. And we have no idea what they're going to do with it. They kept all the employees, but they may just, like, whatever. Who knows? This was pretty stable. We had, and they were giving academics access to it, which is how we got so much time on it. But, you know.
There is like a programming model. I can, if I'm on a PIM, I can know what my PIM is, what number I am executing on.
Yeah.
There's like a way to do all of this
Yeah.
in practice.
Yeah. Yep. Okay, good. So sure. Okay, so you know, I sort of led you down a path where we defined this, and it kind of was an abstraction of what that UPMEM system looked like. Okay, but that still doesn't make that necessarily an interesting model of computation, right? Because what do we know? We know from decades of work decades ago on PRAM emulation that I could still choose to program this whole thing as shared memory, right? And we have emulation results for that, right? That says if I take my overall memory and I randomly hash it, right, and you know, I have a little bit of parallel slackness, so I can you know, hide sort of you know, log p of these things per each in flight at a time, then I can emulate, in this case, a PRAM algorithm, right, on a distributed memory. All right. So if that were a reasonable thing to do, then there would be no reason to have a model that has two sides to it, a shared and a shared. You just yeah, you'd say, oh yeah, the machine looks like that, but I'm just going to program that as if it was shared, right? Which is the whole thing's a shared memory. All right. Can anybody see the issue with that?
Locality matters, right? PRAM doesn't say where it's going to go.
Yeah, in particular, the whole motivation for this was locality, right? The whole reason I built this hardware is to reduce data movement, and now you're going to tell me that the way I'm going to program this is just ignore what moves data and what doesn't, right? It's just crazy, right? So it's like once you tell me that okay, this is just saying that you do the hashing, you do it's provably load balance and blah blah blah. But again, all memory access are now low local. Why bother to have PIM, right? If you're going to do that kind of style of program anyway, you know, then the whole idea of bothering to have PIM at all is just thrown away. Okay? So now I will get you back to this earlier question, right, that says I could just treat the entire distributed memory model, right? Basically, if the bulk of what's going on is at this end, right, you know, and ideally that's true, right? I've got these things cranking away in parallel at the local memories, everything's good. This is not being used very much, right? Then that's the way I should program it. Okay, and as was noted, right, there's zillions of papers on that. So we could do it that way, okay? So what's the problem there? Well, the problem there is that this stuff is actually quite valuable, this side, and you don't want to ignore it. And that's kind of the key message of the work we've done in this area, right, is use this. This is powerful, okay? Don't just treat it like this. It's only this.
It's powerful because you can get data to the core quicker from there than.
It's powerful because this is yeah. So we said this access is considered fast, right? This is fast. This is fast. This is fast. This is slow, right? So you've got access. You have a limited amount. It's a limited amount, but you have some amount that you have a lot of cores here, right? And they don't have to worry about, you know, distributed private memory stuff. It's all shared, okay? And so this is really important to use, and this coordinates everything, right? So this is really like if you have you know, queries or whatever workload coming in, it comes in here, right? So this sees everything. This is the orchestrator of the whole thing, right? And it's got you know, a lot of compute power here, and so you know, make use of it. Okay?
Question? In terms of scale, how does the M compare with N and the cores there compare with the P? Is there something as a
Well, again, that's going to vary from device to device, but again, the P is over 2,000, so that's what makes it kind of interesting as a parallelism platform,
okay.
right? Each of these has, if you want numbers, each of these has 64 megabytes of memory, okay? And last level cache on their host front end, I think is 22 megabytes. Okay. Okay, so it's distributed memory with a powerful shared memory front end. Okay, and think of the compute as you want to do it bulk synchronously. You want to offload the compute. It's kind of, when you program a GPU, you have to offload things to do, or other accelerators, you offload things and you get it back. Okay, so I touched on this when I ran through the key takeaway slide, but the nice thing about pulling data to compute is that you don't really have to worry about if the data use is skewed. In fact, it's actually helpful if it's higher in cache hierarchies and things like that, right? In this world, again, if the data, if you put the data, you've placed data in amongst these PIM modules, and now some workload comes in, right? Like we're doing a lot of work with indexes, so you've got a bunch of queries that come in. If all those queries want data that's on just a handful of those local memories, you're in trouble, right? Because that, the extreme is that all the data you want in a particular round is on a single PIM module. So you basically serialize the whole thing, right? That one PIM module has to spend its time absorbing all that queries and producing all those results, and all the other ones sit idle, right? And in general, it doesn't take much skew in the workload to really mess up the utilization of the system, the parallelism you're able to actually achieve. Okay. Okay. So what we often do if we have sort of hotspots of data is we say, oh, gee, let's alleviate that. Let's take the data and let's move it somewhere else. So we'll somehow avoid, if like everybody wants this data, let's now dynamically take that data and scatter it, right? So that the next time everybody wants similar data, it'll be scattered, all right? But the problem there is that's data movement, right? And that's what we're trying to avoid, right? So any of these sort of approaches that we've used in the past for taking data and migrating it to recover from hotspots, migrating to other memories to recover from hotspots, that's communication. And again, that's what we're trying to avoid. Okay. All right. So, and what we argue is that this tension is inherent, right? It's inherent tension between achieving load balance and minimizing communication, right? That's one of the key challenges of this whole area, right? In fact, it just sort of distributed side of it alone that has this challenge, right? Okay. Now, one way that you could, if you had a read-only workload and you had enough memory, then one way you solve this is by replication, right? You could just replicate the data. So it'd be on all the local PIM models, for instance, right? We don't have enough memory to do that, but if you did, you could do that. But then you're talking about how am I going to handle writes, right? How am I going to handle updates? Because then I have to update all these copies, and that's a lot of data movement, right? And so it's really, our Venn diagram really has three pieces to it. You want to be load balanced, you want to be have minimized communication, and you want to be space efficient, right? Which space/update efficient, right? They're sort of similar, right? Once I replicate, then I have a bunch of copies I have to update, and that makes updates inefficient. Okay, so questions? I know you've been asking a lot of questions as we go, but questions on that first part? Yeah.
Does the AMPC model
You familiar with this? It's the, they take the MPC model and then you have access to, like read access to a set of keys that were distributed in the last round. And is that model any of what's going on here?
Yeah, I'm not familiar with that model. The MPC model, I am familiar with. So the MPC model is, all you care about is the rounds of communication. So in each round, you can do an arbitrary amount of computation, and when it's time to exchange data, you can exchange an arbitrary amount of data, right? And what you really care about is how few rounds does it take to do that? And so this, right? I think it should be clear why that's not a good fit for this, because we're trying to minimize communication. That's saying for free I can communicate everything as long as I just do it in one round, right? But I'd be interested in talking to you about that variant that you were mentioning after the talk. Okay, so so we've started looking at different kinds of indexes. Indexes are always important, but the main advantage that you might say they have is that they're trees. Okay, and so trees are easier to partition, right? Without into pieces where you don't have a lot of communication between the pieces, right? They have good, you can planar graphs would be similar. Right? You can cut them into pieces, and there's not without such that there's not a lot of edges that go between the components. All right. So it's very natural to look at trees because you can't do trees well. You're probably sunk. All right. So and B plus tree is like the workhorse of the database systems. More generally, it's an ordered index that supports things like predecessor and successor. Right, that's what makes it ordered. Right, it's not just doing hash lookups. You need to be able to find, give it a key and find the predecessor or successor to that key. Okay, and you also want to do ranges and things. Okay, so there was a prior work, one of those two prior works that I mentioned at the beginning, that said, let's look at doing an ordered index, where we do the most natural thing is we just take the key space, right, and just partition it at different boundaries. Ideally, these would be the quantiles, right? So in this picture, I'm only drawing 4, so you'd want the lowest quarter of the keys here, so forth, so forth, so forth. And then and then their proposal was to just do little skip lists in each of the PIM modules, right? And so the nice thing about this is that when queries come in, you just have to send it. Oh, and then at the CPU side, you just keep the root keys of each of these skip lists, right? And so when a query comes in, you say, oh, it's a query for 10. That means it's got to go, and I'm trying to find the predecessor of 10. So let me send it to the 7 node, and then from there it can get the answer. Okay. And so, if your workload is nice and uniform, everybody's happy, right? Because you get a batch of keys, and they get spread evenly, randomly over all these PIM modules, and you can get the good utilization, right? But clearly, what can go wrong? Yeah, you don't have that beautiful, uniform random workload, right? That basically have a realistic workload where maybe everybody wants to know predecessors between 7 and 25, 24, right? Yeah.
Are you at all worried about range queries crossing the modules, or is that not a problem?
So in this case, yeah. So typically, what we look at is sort of short ranges that cross maybe at most one module. If you have a really big range, then yeah, you could just broadcast and get the pieces, pull them together. Yeah. Okay. Good. So again, here's the example. Suppose the queries is I want the predecessor 7, 8, 17, 22. They all end up here, right? So you've got three PIM modules idle, and you've got one having to do all the work. Okay. All right. So let's flip it around. Let's say, okay, well, if randomization is good, right, then if for defeating bad workloads, right, let's just take in this case skipless, and let's just take every node and just throw it randomly somewhere, right? So at least now I know that kind of, well, or it seems like I know that this is going to resolve the load imbalance problem, because now the adversary doesn't know the random placement of which the mapping to PIM modules, and so things are going to work out nicely, right? So what's wrong with this? Well, I still have these pointers, right? So, the host front end can store maybe the first few or whatever, and then this pointer has to be a pair. It has to say the PIM module and then some local address within the PIM module, and that's what we do. Yeah, we do that for all our pointers are that style.
Can you solve the queries within the PIM module?
So each query now is going to have to bounce around between a whole bunch of PIM modules, right? So this is rounds of communication just to get from here to here, right? And so this doesn't work, right? And not only that, this actually doesn't really solve the load imbalance problem. I'll give you an example in a few slides. It just looks like it does, so you end up with log n, if there's n keys and binary, you end up with log n communication per query, right? And we want something more like constant communication per query. Okay, we want to just send the key we're looking up and get back the key that's the answer, right? The key and the value that's the answer. Okay. So what I've shown you is that if you do range partitioning, it's space efficient, update efficient, right? You only have to update the one copy of the data. It's good at communication reduction in the non-skewed case, but you don't get load balance. And random mapping is good for, again, space efficiency and load balance, although not really, but at a high level, it's much better at load balance, but it's terrible at communication, right? So what's a solution that would lie in this space?
Are the ranges small enough that?
Yeah, for the most part. In the workloads that people care about, the ranges are small. Yeah. If not, again, you can sort of broadcast to, like the host, again, the host CPU knows like where things start, and then it says, oh, I need to broadcast this query, this range from, if it's from, I define the ranges as being you're given a left key and a right key. So I know what it is. If you're given a left key and a number to return, then it's a little more tricky. But if the host front end knows how many keys are in each place, it can still figure it out.
Can you take sort of blocks of keys and small enough blocks of keys and then randomly place them around? Would that help?
Yeah, we're going to do something along those lines. But let's finish with my question here. So what would be an example of something that can achieve load balance and reduce communication?
So I want to do range partitioning, but then balance load by caching on the CPU side.
So
that's not space efficient.
That I only have, in part we'll do a little bit of that, but I only have a limited amount of shared memory.
It depends on how skewed the data is, right? So
Yeah.
if the hot stuff's really hot.
Yeah, but the intuition is right, okay? The intuition is, and we'll get to that in a few slides, distributed, having a bunch of local memories is really bad for concentration, like hotspots on data. The front end is great for hotspots on data, right? You've got the last level cache there. And so that's an example of how we really want to use both sides. Because when the data gets really hot, we definitely want to have it on the host side and just absorbing all that work. Yeah?
Could make multiple copies?
Yeah. Yeah, so this is that full replication straw man I drew before, right? If you had this space, if you blew up, if the machine provided the space such that you could take your set of keys and replicate them on every single module, then yeah, it's easy to get load balance. You just round robin queries or whatever. there's no, the communication is low, you just send a key, you get back a value, there's not rounds of communication and so forth. So we know how to get 2 out of 3 readily, right? And the question is, can we get 3? Yeah?
For common like data set sizes and memory size, how many levels of the skippers are actually on the
Could you repeat the question?
Yeah, so for given data set sizes and sizes of these memories, how many levels can we expect in the skip list? Part of it depends on what the base of your skip list is. So I've been drawing binary skip lists, right? You can draw skip lists that have larger bases, right? They could have like 16-way skip lists, and so it's sort of the log of 16. One of the nice features of the solution that we're going to show is that well, let's see. So, I mean, it can, the overall skip list, even with a base of 16, can have like 6 or 7 levels, right? And you know, we're trying to avoid those rounds of communication. Things like that. Yeah. Good. Okay. So can we get all 3? So, all right. So, so we had a paper. And this is the stuff that Hongbo is going to talk about. So try not to steal his thunder too much. But basically, the first step is we say, well, the top part of the tree, the top. You know, you can go from the root all the way down to, or let's say, start from the bottom. The first log p levels are down here, and every level above that's up here. So the number of nodes up here is only order n over p, right? This is the way the trees work, right? The top log n minus log p levels together only have n over p nodes, okay? And so we have n over p memory in each local PIM module, and so we actually can do full replication up here. Okay. That doesn't blow up our space bound, and it also doesn't blow up our update costs. Why? Well, what causes a skip list stack to go up to this level? You have to, in the binary case, right, you have a half probability of going here, half here, and half here, and half here. To make it over up log p levels, you have to, that's only a 1 in p chance, right? So, you know, an expectation, 1 out of every p inserts is going to want to update something up here, right? And so, yes, you do have to update all p copies if you do it this way, but it amortizes out to constant per insert. Okay, so again, we're able to replicate this fully because it's small and it's not updated very often. Okay. Okay. So that's good. So now we can solve contention at the root and all these top parts or whatever by just round robining, right? We can take our, suppose we have a batch of queries, 1, 8, 9, and 10. We can take them and round robin them across the modules. They all have a full copy of the top part of the search tree, and so they can all traverse it, right? Okay, and then what they send back to the host front end is you know, where did things play out? Like, what's the next node they want to hop to? Okay, and so we can see that 1 figured out it needs to hop here, and you know, all the rest, though, 8, 9, and 10, all need to hop to this 7 node. Okay. Okay. So so if you were just to naively continue the process, then even though this bottom part, as I've drawn it so far, I've just randomly scattered the PIM nodes. So you think, oh, random scattering, it must be good, right? It must be good for load balance. No, because all 3, you know, 75% of my queries wanted to go to this node, right? So yeah, this node is at a random place, but it's hot, right? And notice these aren't duplicate queries. I can't just like, oh, if I see two of the same query, I'm just going to fold them together, right? No, this is 3 different queries, and they all want to go here, right? So that's a problem, right? So even with random mapping, didn't solve my load balance problem, okay? So what do I do instead? Well, all right, so this case was fine. I only had one, I had there's a threshold I'm going to have. And if the number of queries that want to go to a particular node is below a threshold, I'm going to go ahead and do it. I'm going to say, OK, good, go ahead, do it the PIM style. But in this case, I'm going to go the other direction. Right? I'm going to pull, so this is push, this is pull the data back here, right? So now I could have as many queries as I want that wanted this node. It's not going to cost me any more communication than the cost of just sending that node back this way. Okay? And so that's like this, this general theme that we can take advantage of, this algorithmic trick, right? It's not either processing in memory or traditional, von Neumann style, pull the data to where the compute is. It's both. And you want to make it both, and you want to make it both dynamically. Right? You want to decide as the computation is going along, independently for each node, right? Which moves less data? Push all the queries that want that node or pulling the node back? Okay? And so if it's this, I'm going to do a processing memory thing. If it's this, I'm going to do the traditional von Neumann thing. Okay? And as we just discussed earlier, this is great because the host CPU loves hotspots, right? It's a limited amount of data, right? It's just the most number of nodes you're going to pull back is the number of queries, right? Or some significantly less than the number of queries. We're assuming that the number of queries in a batch always fits within our memory. Okay, that's a reasonable assumption. And so it has enough memory to hold one round's worth of hotspots, right? And again, the general principle is that each side has complementary strengths. You want to design algorithms that exploit the strengths of each. OK. So in reality, I've talked about this replicated top layer. I've talked about this random bottom layer. We actually have a middle layer where we do a partial replication to avoid having to do a bunch of hops in this middle part. Hongbo will tell you a lot more about that. We also, instead of doing a binary skip list, we do a B area where you promote to the next level up in the skip list with probability 1 over B. Our implementation uses B equals 16. And the net result is that the amount of communication per query is reduced to this expression, log B of P. Given the earlier question, right, this bound is 3 in practice. Okay, so it's a constant amount of communication, roughly 3 words in practice, is what the end result looks like. And again, it's this combination of sort of chunking things and moving random chunks and things like that, right? Good. And the code's available. OK, so what we've shown now is that, so we have theorems in the paper that show as long as the batch size is something like this, right, P log P times B times log base P of P, then we can guarantee against any adversary that we will get load balance throughout the process, that all the I/O is load balanced, all the work on the PIMs is load balanced. And our basic assumption is still linear. Yeah?
So how do you update in this scheme? How do you support updates? Because
Yeah.
you have all these replicated data.
Yeah.
Is it linearizable?
Yeah, well, we're doing batch parallel.
Could you repeat the question?
Oh, how are updates done? So we're doing everything in batch parallel, right? So basically, we take, if you have inserts, we'll take an entire batch of inserts with nothing else but inserts running, right? And again, this is sort of stealing some of Hongbo's thunder, but one of the reasons that we use skip lists and not other things is skip lists, you can know for each insert what height of the tree it's going to be, right? Because that's just a coin flip, right? And so you know before you even start to amend, patch the skip list structure, you know exactly where things are going to go. The CPU host knows, oh, okay, I need to patch up this level here and here and here, and this level here and here, and so forth. So that foreknowledge enables you to just say, okay, go do it, right?
Okay.
And we don't worry about the concurrency issues because it's batch parallel. It's all just inserts, right, at a time, and then you have a phase with queries and things like that. Okay. So the key thing to make this work is a weighted balls and bins theorem, right? That basically says that if the maximum ball you're throwing is less than something, the average total weight of the balls, then you're guaranteed with high probability that things are weight balanced, okay? And so the key is getting this maximum low enough so that things work out, and that's where push-pull search helps, right? If we didn't do push-pull search, the maximum we could not bound this maximum, but because of push-pull search, right, we're able to say, oh, okay, well, the times I push, I know that's only so much work I'm pushing, right? Okay, good. All right, so this is the UPMEM system. People were asking about that earlier. Again, it has normal DRAM, and it has this PIM-equipped stuff. It's a pretty simple processor, runs at 450 megahertz. That's a sixth of the speed of a normal processor. Scheduling is done by the programmer. And so we have results that are completely unsurprising that says that as you increase the skew in your predecessor queries, it can be done for any of these ones, what is the skew? Like Ziphian 1 is like the skew of words in say, English, right? What is the distribution of those? As you increase the skew, our approach, PIM tree, is basically flat to skew, right? This is throughput, so high is good, all right? The partition skip list that I showed at the very beginning, yeah, it's great if there's no skew. If there's absolutely no skew, it's going to beat us, okay? But very quickly, again, realistic skew is in this range. Very, very quickly, it craters, right? It just falls apart, okay? And even by here, it's like here I said this is sort of realistic. We're already 31 times faster, right? And the curve just would shoot up and up and up. So that's versus other PIM-based things. We also have results versus shared memory indexes. So we did the Bronson, the Brown A-B tree and the Bronson tree. I'll let Hongbo describe these graphs in more detail, but the punchline is that this is communication. This is bytes transmitted per element. And our approach, well, there's different flavors of our approach, but the main one to focus on, I guess, is this purple and well, either of these. These are both our approach. We're much lower in communication and slightly better in throughput, right? So this is the goal, right? We're trying to save energy. We're trying to move less data. This is kind of just a bonus, right? That we actually are faster as well. Okay, and Hongbo will give you all the details about that. Okay, and again, note this is a first-generation PIM system, so there are definitely huge engineering bottlenecks in it that make these numbers worse than what they could be. Okay. Any more questions on PIM tree? Okay. So as I noted at the beginning of the talk, we looked at a bunch of other indexes. We started with radix trees, right? You store a collection of strings in this trie-based structure, and you want to answer longest common prefix and queries and things like that, and be able to dynamically insert it and delete it. So it's still a tree, right? We have PIM tree, which works for trees. But there's a couple things that are very different about radix trees and tries. So one of them is they can be highly imbalanced, right? So we constructed our skip list probabilistically so that the height of all the leaves is about the same, right? But the height depends completely on what strings you store. So if you store a bunch of strings that all have common prefixes, this trees can be highly skewed. And so our tricks for that work out easily because we're starting with a tree that's balanced is challenged by this setting. The height of this tree is now the length of the longest key, right? So that's a problem. And in fact, if you look at prior approaches to this problem, they tend to suffer from some complexity measure that's order their height, right? So if you have skewed collection of strings you're storing, you may not be getting much parallelism at all, right? You're sort of serially bottlenecked by this really long height. The second challenge is that, again, we want to do this in batches. So we don't want to do redundant work for the queries in a batch. So what we do is we build a try on the set of queries in a batch. So now we have one of these, this encodes 4 different strings, right? And this was the batch of queries. And then we have, stored as our index, the try for all the queries, all the keys, right? So this is the queried keys, and this is all the keys. And now we're trying to do this matching. We're trying to find where in here is a corresponding thing in here. But as this illustration notes, just because there's an internal node in a try for the prefix 0, 0, because you have multiple strings that you're looking up that start with 0, 0, and then they diverge from there, doesn't mean that in the full data set that there's going to be a similar node, right? So you're trying to match this try node in the query batch against something that actually falls on an edge, right, in the overall structure. Okay, so that's one of the key challenges in doing this sort of try versus try matching kind of policy. And Hongbo is going to tell you about that. Iwei is going to then follow and talk about our work on spatial indexes. These are things like KD trees, right? You have the points and you do split along dimensions at medians, and you get this tree. And now you want to do spatial kinds of k nearest neighbors and spatial kinds of lookups. He's also going to talk about a more ordered version of this, right? Where instead of doing the KD tree trick, you linearize the space with a Morton order, and you build a tree on top of that. Okay, so again, see his talk for that, how to do that well on PIM. I have another student who's working with UA, has been building a database, transactional database on top of PIM. And so here it's interesting because, again, PIM is a 50-year-old idea, including in the database community. Everybody says, oh, PIM is perfect for the filtering that we want to do when we're doing queries, right? You want to find something in the database that has some property. You have the select clause, and you want to find these things. And so why not, do that where in PIM, so that the actual number of database rows you ship back are much smaller, because you're only shipping back the ones that actually match the query, right? In the traditional database, you'd bring in all the rows one at a time, right? And you'd see, oh, this one matches, this one doesn't match, right? But that's not transactional workloads. That's what's called an analytic workload, right? You're doing a read-only query over the large database. And so there was this notion that in the database community that, or just anybody that's looked at PIM, is they always just thought, oh, well, clearly we're talking about filtering, right? We're not talking about transactions, right? Transactions is like, you update your bank account and stuff like that, right? And so what this work shows is that, no, you can actually do transaction stuff well on PIM, okay? So what we did is we looked at every single component that a transactional database system has and every single data structure, and we decided, do we want that data structure stored in the PIM memory, or do we want it stored in traditional memory, okay? And the the policy for doing that was pretty simple. If you suppose you want to traverse an index, right? If you just keep that in the normal memory, then of course all the lookups on this path, we just got done talking about PIM tree, those would all be fetched, right? So that's a lot of communication. It's the height times the node size words of communication. And in the PIM, as we've seen, you can actually do, this is sort of the idealized thing where you never come back from the PIM until you have the answer. Okay, and so that's this much communication, right? And since this is much more than this, you want to put your indexes on the PIM side, right? Right, large advantage using PIM. And so and then there's a thing, databases, transaction databases do multiple versions of data. So you can do, you could be updating the data while queries are getting consistent snapshots of the data. That creates something called version chains, where you have for each data item, not just a single copy, you have a time-stamped copy. Okay, this was the copy that was valid starting at time t. This is the copy that's valid starting at time T1, starting time T2, starting at time T3, and so forth. And when a query comes in, you just go down that version chain and find the version that was visible when that query started, right? And so if you do that, that's, again, chasing pointers, and you want to do pointer chasing on the PIM side. On the other hand, fetching a tuple, right? Fetching a tuple is, I have some pointer of that tuple, maybe it's the key of that row, it's a lookup. It's not like an ordered index predecessor search. In DRAM, it may just be a load. You just you load the data in that tuple. In the PIM, even this part, which is sort of taking the data from the PIM, the row from the PIM, and sending the result back to the CPU. This is a fetching of a tuple. It's also tuple size. So there's no communication advantage to storing tuples if all you're going to do is do a lookup and grab it, right? And so there's no advantage to PIM, and it's also disadvantage because this offload is expensive. There's offload overheads. And so you want to put the tuples on the DRAM side. Okay? And so doing that kind of thing and figuring out all the logical components. This is probably too busy of a slide, but this is talking about databases have log files and they have transaction managers to decide whether transactions can commit or abort. You've got the different queries doing their thing, get, update stuff, commit, and things like that. You have to be careful about how you lay things out and how you do how you orchestrate things like garbage collection, a version list, and things like that. But it can all be made to work out, okay? And the end result is, again, what we were aiming for was reducing memory traffic. So this is a comparison between running our system, OLTP PIM, on the UPMEM system, so you've got processing memory, versus running the state-of-the-art in-memory, shared memory database, running on the exact same platform, but with the PIM turned off, right? Not using the PIM, okay? More precisely, just putting back in normal DRAM where all the PIM modules are. So it's the exact same front end, exact same number of memory channels and so forth like that. So it's a fair comparison. And the communication is reduced on these two sort of standard benchmark workloads that just doing a bunch of sort of lookups and things. We're 5 and 6 times less data movement, right? So that's good. And this is the kind of the bonus. We're actually also faster, right? 70% faster in these cases. Okay. Now we don't always win. There's issue. These workloads are read heavy. If there's a lot of writes to the workload, we start to lose, not because there's something fundamentally wrong with writes, but because there's something fundamentally limited about synchronization on the UPMEM system. And so it doesn't have a good way to grab locks, or it doesn't have synchronization primitives. Has very restricted synchronization primitives on the PIM itself, and so you get bit by that if you're doing a lot of updates. So it's not fundamental, but it's in our minds it's nothing fundamental. but it's just the reality of that current platform, the first generation platform. Okay, questions on that? Yeah.
So is it not possible to play the same trick in terms of offloading the things that PIM is bad at to the host? So if the problem is restricted synchronization primitives and it's better on the host, can you take highly contended on blocks and...
That's, so the question is, can I, if synchronization is bad on the PIM side, and we know it's good on the host side, can we do that synchronization on the host side? We didn't look at that. That's an interesting approach. All right. So I want to spend my last few minutes talking about this distinctiveness revisited. Okay, I made a huge point at the beginning of the talk explaining why PIM is distinctive. Okay, so as a thought exercise, all right, suppose I said, oh, well, I could take my distributed system, right, distributed memory, and I can elect one of the people to act as the host, right? One of the nodes acts as the host. Run my algorithms that way, right? Why can't I take all these algorithms I just developed for PIM and just mimic it by just picking a host, right? And saying, oh, you're the host. You do the stuff the host does. All the other ones will act as the slaves, act as the workers. And certainly functionally that would work, right? Right? The question makes sense, right? It's sort of saying, let's step back and say, well, if it's good to have a coordinator, right, and do these active passive things, can I just do that in any distributed setup, right? And the difference is, so this node here, I mean, it falls out very naturally from the UPMEM system, but just generally for our way of modeling this system, is asymmetrically powerful, right? It has asymmetrically more bandwidth because it can, in one round, communicate to all these guys, right? And receive from all these rounds. And it can also keep up with all, like they're producing work, right? Answers come back. I've said, oh, this guy just turns around and fires off the next round, right? That means this guy has to have computation power that's asymmetrically large, it has to be able to keep up in some sense, right, with all these guys, okay? And so this makes sense because when I didn't have, the first thing about the asymmetric bandwidth makes sense because it was true in the non-PIM world, right? Like if you think about your normal processor, right? It's got as much memory out of the host, out of the multi-core as it has, as all the other guys can receive, right? Otherwise, there would be no. There's sort of a balanced system assumption, right? The host design is designed to keep up, right? It's designed to keep up in terms of memory traffic, right? If you couldn't send out enough traffic or receive enough traffic from the host to match what could be received or sent by the other end, then you've sort of you have an imbalanced system which would be inefficient, right? You wouldn't want to pay money to build a system that way. Okay, and that's why the I/O time metric is the max from 2ME PIM module. It wasn't the max coming in or out of the host front end. Okay, yeah, and similarly, the work this has multiple cores in it. It's much more powerful, much higher clock speed, and so forth. So it can tend to keep up with this. And in fact, we have a graph that shows, what fraction of the time. If we don't pipeline things, we have some pipelining things. If we don't pipeline things, what fraction of the time in our predecessor queries, for instance, are we spent on executing in the PIM, on the communication between the two, and on executing on the host front end, right? And we can see that the host execution time is 1/4 to 1/3 of the overall time. So it's not nothing, but it's not dominating. It's not like the CPU is falling behind. the host is falling behind. It's keeping up, right? These bars are on par with the other ones. All right, so that shows in the system, the UPMEM system we're using, the host is sufficiently powerful enough that it's keeping up, right? It's not getting blown away by the other ones. Okay? Again, so there's this asymmetry, and the question is, how much asymmetry do we need? Right? So the model has factor P asymmetry between the host and the PIM modules. We've shown that we can get away with P over polylog P, right? So if there's like if the host is say only P over log P, more powerful, has more bandwidth, our algorithms work just fine. But we don't know what's it's an open problem to know whether that's the lower bound, right? Is it possible to have a front end who has less than this advantage in bandwidth and still, I mean, you could define what's the context of this thing, but you could take a problem like indexing or something and study whether you need, in order to get the bounds we have, or similar bounds, you need this asymmetry. This number doesn't surprise us because, getting back to the MPC model, there is a paper that we saw on a heterogeneous MPC model where you have one of the MPC nodes being some factor more powerful than the others, right? And their results, at least they only have upper bounds like we do, show that if once the more powerful MPC node is this much more powerful than the others, then lots of problems get easier, right? The lower bounds for number of rounds, change significantly, right? And so maybe there's a similar, I think we need a lower bound in this world too, but it'd be nice to have a similar result in this bound. But it makes us believe that at least there's some evidence that this is kind of what the bound's going to end up looking like. Okay, and finally, there was some talks we already seen on CXL. Okay, so CXL is this way of having passive memory, a pool of passive memories that different processors can latch onto. So this is showing like you have this space where you have 1, 2, 3, 4, 5, 6, 7, 8. You have 16 of these nodes that just have memory, and they're sort of sitting there passively. And you can the overall system can decide that, I'm going to give 6 of those nodes to node 1 to sort of compute server 1, and so forth, and this many to blue and this many to yellow, and that can change, right? And so that allows a lot of flexibility, and so a lot of vendors are providing this now. You can also share things in a disaggregated world, right? You can have completely different programs, completely different virtual machines or servers or whatever, and they can access the same object and so forth. So that's CXL. That's definitely happening. What we're looking at is a possible future where you actually equip each of these little guys with compute, okay, and sort of run in our coordinator worker style of the model we've been talking about today. And in fact, there is I guess it's called a pre-product out of Marvell that has exactly this. So they're proposing that this chip be placed, with each of these, and it's got, again, it's much more powerful, right? Because it doesn't have the constraints of the little DIMM, but this has 16 cores, and they're reasonable cores. They have floating point and SIMD and things like that, and so this world is on the way, and so the question is, we believe that the ideas and the model that we have fit this world as well, but we haven't played around with this platform yet, and we'll see if there are any interesting questions that arise in this different context. Questions on that? All right, so here's the team. You're going to hear from Hangbo in a minute, and then you're going to hear from Yue after that. This was from the first paper we wrote. The processing memory model was a virtual conference, so he's actually giving the conference presentation the first slide of his conference presentation, and I superimposed the pictures of everybody else. And so again, the key takeaways, data movement is the dominant cost. I don't think that's going anywhere. Processing memory is a way to reduce it. I've argued that the PIM is unique. It has both a shared memory and a distributed memory in sort of a coordinator worker style. We've advocated for this processing memory model as one way to think about that. You have shared memory metrics, you have distributed memory metrics. I've argued that the host is big reason it helps is because it has asymmetrically high compute and bandwidth compared to the guys here, right? And that's kind of somehow baked in. There's this inherent tension in processing memory between load balancing, communication, and space for skewed workloads. Push-pull search is a really cool way to do things, right? And you can imagine applying that kind of strategy to any kind of compute, right? Not just search, right? To just decide on the fly what's going to move less data and do that, right? We have analytic guarantees. It's much faster in practice. We've looked at all these other kind of database-y, indexy kind of things, and we have some open directions we're pursuing. So with that, I will stop. Yeah.
So I want to go back to your slide where you said there was 2 algorithms papers in this area. So
okay.
One difficulty as an algorithms researcher when you see this is, you'd like to find an algorithmic problem in which you can do an interesting algorithmic solution in this model.
Yeah.
And one problem you have with these different models is, like, if you pick a random problem out of your algorithms book, it's difficult to do something in this distributed model, whatever it is. And one of the things you found is, like, you have data structure stuff here. So, like, imagine you're an algorithms researcher who wants to contribute to algorithms in the PIM model. Like, what else might you try to find an algorithm for besides data structure-y things you have?
Well, I think there's plenty more data structures out there that you could look at, right? I was trying to hint that each sort of adds a new complexity to it, right? I mean, and so yeah, so you could.
If you don't know, this is fine. I was just.
Yeah, I mean the.
I can suggest one direction is you look into some workloads that's memory bound. So try to find something that's memory bound. You can probably get something from that. But if it's not memory bound, it's very unlikely you can get anything from that.
Okay, but like, as an algorithms guy, what I want to hear is minimal spanning tree, or this is an algorithm problem. Like, memory bound is
That's
not
harder.
a problem. So
That's harder.
Yeah, I mean, I think because the bulk of the work is being done in distributed style, anything where the underlying graph of the problem is not separable, well separable, is problematic. So I would start with problems for well separable input graphs.
So I think there was a paper like a few years ago on how to put data structures on PIM, maybe PODC disk spa something, and if I'm not hallucinating too much, maybe you remember it better, they had like, you were duplicating all the top tree level, they put the top levels on the CPU.
Yeah,
maybe
that's.
you can compare, say what's...
In practice, that's probably what you do. Our model has a parameter m, which is the limit on the amount of memory. So if m is smaller than n over p, then you have to do it the way we described it. But in practice, it's probably not, and so you probably just put it in this shared site. Yeah.
In general, you know this paper and you can
Yeah, I
say
think
something
it's-
about the differences? Or?
I think it's in spot like 2022, like.
I think it's one of the two with your
Yeah,
previous data.
no, it's like the follow-up work on those 2 papers.
Hurley, right?
Yeah.
Right,
Yeah, that's one of the 2 he was mentioning.
Well, I think it's a follow-on, but.
Yeah, it's like there has been like two prior papers, and one of the author like they follow up on these 2 papers. So that's the only 3 papers other than our work. And I think one of the other key differences might be that, as you can see, we have like 2,000 PIM modules in total. And if you aggregate their compute power, although each of them are single core and have like 1/6 of the frequency, but if you aggregate these 2,000 of them together, the overall computation power must be much more powerful than like any 64 core like CPU on that. So it depends both on like how much your cache size is compared with the single PIM module, and on the other hand, like the aggregated computation power in practice must be considered.
So basically, it's the power of the
I would say
different
both.
components.
Yeah, that's a good secondary point. So it's do you have the space to store the entire top part of the tree, and do you would it actually, if you have however many cores beating on that, does it actually outperform having 2,000 cores in parallel doing your search for the top part of the tree?
That's the main difference.
One more question, we're quite a bit long here.
Yeah, sorry.
I think this is a related question, but so we're seeing similar kinds of things moving compute to storage.
Mm-hmm.
So what changes in the current results if I have SSDs with these processors instead of PIM modules? And I think it's a combination of these things, right? It's the ratio of M to N, but it's also the number of processors P, because I probably don't have as many SSDs as I do PIM modules.
Yeah.
But is the right thing to compare M compare M to N over P? Is that the right?
So I'm setting this up. The question is for things like computational storage, where you have compute embedded with SSDs. Do some of the same considerations apply? And the answer is yes. I think that model, this model fits that world as well. So yeah, similar considerations would apply. It's just in that case the disk is the the storage part of things.
Right, but I might not have 2,000 SSDs, right? So
Yeah, you have to look at the aggregate computing power you have. But also, I've sort of set up a straw man in this, said you either store the entire top half in the shared cache or the entire top half in PIM. But in reality, you might store, depending on the compute power, you might store what fits, the top part that fits in the M, right? And then the next part replicate it and so forth. You might, it's not either or.
All right, let's thank the speaker again. All right, coffee break.